Now we are ready to meet a feature of the language that is among the most important we are going to see in the entire course, and a feature that's going to follow us all the way through until the end. And not only is it a very important and useful feature, but this video is also going to be, I think, our first exposure to the biggest shift that we have to make in our mindset between C and C++. So in C, we certainly, by the time we got to the end of CSC 111, where we're working with a lot of pretty detailed stuff, linked lists and arrays and strings, we're still writing programs that are basically code logic that's throwing around plain old data between functions. And so we'd have to take our array and pass it the array and its size to a function. The function receives the array and its size and operates on it. But ultimately, there's this huge gulf between the code logic, the functionality, and the data. They're kept completely separate. And what we're going to notice in this video is that in C++, there's a different way of thinking about the world. Instead of a bunch of buckets of data that we throw around the program, in a sense, we're sort of thinking about the world in terms of a bunch of small appliances, where each small appliance might have some associated data and some behavior, but it's all packaged up so that we only have to worry about how to use the small appliance. So it's no longer necessary for everybody that observes a given piece of data to understand everything about how to keep that data organized. And so that's the main shift this video is going to illustrate, the shift to viewing the world in terms of a bunch of interacting small appliances. Now, a lot of the higher level uses and features of this new type I'm going to discuss, something called a vector, are detailed in notes that accompany the video. So the notes go over all sorts of other interesting uses of vectors. I just want to go over the broad strokes in terms of the video itself. Although, of course, in the next few videos, in the next few weeks, we're going to keep coming back to vectors over and over again. So the goal of this video is to talk about this new fancy shiny type called a vector, which is a sort of abstract way of storing a sequence of values. Now, you're already familiar, if you're used to a language like C or Java, with storing a sequence of values. So for example, here's a sequence of values that I might make in a language like C. So there's some values. And this would be a C-style array. And a C-style array has indices, and I can access the element of each array using its index. If I ask for index 1, I get this thing. If I ask for index 2, I get this thing. I am welcome, if I want to modify the elements at each index as I see fit. So I could set this to be -7 or something. And we know already that in C, arrays have a lot of limitations that make them very frustrating to work with. One of them is when I create an array, its size is fixed forever. And so I can't make it any bigger or smaller. I can make a new array that's bigger or smaller, but once I've made an array, its size is permanent. Of course, every element of an array in C has to be of the same type. We're going to notice the same is true of vectors in C++. But also, arrays in C, not only is their size fixed, but strangely, almost a contradiction of that, they don't even know their own size. If you want to know the size of an array in C, somebody has to tell you. You can't simply ask the array for its size. We're about to meet a feature of C++ that undoes a lot of those constraints. So a vector in C++ is an abstract way of viewing a sequence. So I might want to make a vector V. And V will start out containing nothing. And then I will add stuff to it. V now has the element 6. And then later it'll have 6 and then 10. And then 6 and then 10 and then 17. And at any given time, I can make the vector bigger or smaller. I could add an element at the end. I could delete an element. It turns out, we'll see later in the course, I can add elements anywhere I want. The vector can grow and shrink. I can make copies of it. I can ask the vector, what is your current size? The vector would here say its size is 3. And so in a sense, this vector object behaves sort of like a small appliance whose job it is to store a sequence for you. You leave it up to the vector exactly how it does that. But if you want to store elements, you can put them in the vector, you can take them out. You can look at them by index, you can iterate over them from left to right if you want to. The vector sorts all of this out itself. You no longer have to worry about the minutia of storing sequences. And we'll see that this is just opening a door to this huge world of small appliances that we can use in this course for all sorts of different purposes. Although we're going to stick mostly to vectors and related things for the first little while just to get used to the notation. All right, so the first thing I want to do is I would like to create a vector that will store a sequence of integer elements. Now, maybe you can satisfy yourself by analogy to arrays that just now I had a vector that contained 6 and then 10 and then 17, which was a sequence of things in an order. The 6 came first, then the 10, then the 17. There's no requirement that the elements of the vector be in ascending order. I could have then 0, then 7, then -1. But when I store a sequence, I want the sequence to be maintained in whatever order I decided to use. So I, the programmer, define the order of the sequence. If I wanted to, I could then ask the vector to tell me what's at a particular index of the sequence or something. One thing you could observe, though, is that the vector could store ints. The vector could also store, I could have v store 6.3, 1.9, 10.2. It could store doubles, it could store floats. In fact, maybe it could store strings. Maybe it could store huge arrays of data. I don't really care. The job of a vector is to maintain a sequence of something. Not necessarily always ints, although in this example we're going to use ints. So I've included the header called vector from the C++ standard library, and of course I need to make sure I always include that if I want to use the type vector. Now I will create my variable v. Its type will be std::vector, and then I write this. So I have created a variable called v, and notice that I have used empty curly brackets, that is uniform initialization. I don't quite know what a vector is just yet, so how do I know what initial value to give it? Well, fortunately for me, uniform initialization can help me out. I use the empty brackets to say, please initialize this vector to whatever the sensible default value is. Now, a vector's job is to store a sequence of data, of any number of elements. And it turns out that the sensible default value of a vector is an empty sequence, a sequence that contains nothing. Now, what's the type of v? The type of v is this strange incantation. We know already that this prefix, std::, is a way of indicating that the thing I'm referring to is in the standard library. Because the standard library is so massive, everything was filed under the std::: prefix to make it easy to identify, so that if you made your own thing called vector, it wouldn't conflict with the one that's provided by the language. But what about this? And you'll notice inside the angle brackets I have the name of a type. The type int, a type we're quite familiar with. It turns out this is because a vector is a sequence of something, but nothing in particular. You could make a vector of whatever you want. And so this is a way of parameterizing a type. So the type of v, I read the angle brackets as, I read that as of int. So I would read this as v is a vector of int. I don't usually read this part because it's sort of implied because we use vectors so often. V is a vector of int. I could also, if I wanted to, have the elements of the vector be doubles. So v is a vector of double. If I wanted to, I could have the elements of the vector be other vectors. So v is a vector of vectors. Okay, but we do not want to talk about that just yet. So we'll go back to this. V is a vector of int. And in general, when you see angle brackets, that's a sign when we're working, at least at this level. When you see angle brackets, that's a sign that you get some input into which types you're working with. What are the underlying types? A vector can store elements of anything, so what specifically do you want to use today? And today I'm making a vector of int. As of the end of line 11, I now have a variable named v, and v is a sequence of ints, and currently it is empty. The default value created by the uniform initializer is that it is empty. Now, one sort of unsettling note is, in this case, if I don't put the uniform initializer, v will still be initialized to be an empty sequence. And the reasons for this are complicated, and they're mostly historical baggage, which is why I'm not going to refer to this any further, other than to say that it is good practice to always use a uniform initializer. Because there are cases, like we saw in the previous video, where omitting the curly brackets results in uninitialized data. Strangely, that will never happen with a vector. And I know it's strange. We'll come back to that in, I guess, week 6 or 7 of the course. But for now, to avoid having to worry about that, we will always use curly brackets. And we know that the empty curly brackets mean create a default version of this type. And in the case of a vector, that's an empty vector. Okay, so the next thing I want to do is add elements to my sequence. So I guess I could sketch what's in my sequence. I'll sketch that over here. So here's v. Currently, v is empty. So what I can do is I can interact with V. V is a small appliance. Its job is to store a sequence of things. And the goal behind the vector type is to make it so that I, the person using the sequence, never has to worry about the internals of the sequence. Exactly how I store a sequence that can grow and shrink, that's none of my business. Instead, I just tell the vector, here's some stuff, add this to the sequence, or tell me what's in the sequence right now. You might recall from CSC 111, one analogy I very much like to use is that of a toaster. Do you need to know how a toaster works to make toast? Well, no, that's the point of a toaster. You take some bread, put it in the toaster, press the button down, and it makes the toast for you. Bread goes in, toast comes out. That's why small appliances are useful. You don't have to understand anything about how toast is made to use a toaster. It might be useful to understand those things for other reasons, maybe recreationally, maybe as a hobby, maybe because you want to design toasters one day. And it turns out in this course, we will want to design vectors one day, so it's useful eventually to understand what's going on behind the scenes. But when I'm not designing it myself, when I'm not designing a toaster, if I'm tired and it's early in the morning, I just want to make toast. So I put the bread in and I push the button down. I don't worry about what's happening internally. Now we're going to come back to that analogy later because that analogy can be taken quite a bit further, and it should. But in the meantime, let's think about the vector as a small appliance. So now I want to add some elements to the vector. I don't care how the vector does this, I only care that I can do it. So I write this, v.pushback, and then I give it an element. Now v is a vector of ints, so when I give it an element, I suppose I should be providing an int. So I'll do 6, and then I'll push back 10, and then v.pushback. Now the operation pushback says add a new element, the one I provide, to the end of the vector. We'll see later in the course, although not for vectors, that there is an analogous thing called push front, which is to add to the beginning of a sequence, but pushback is to add to the end. So as of the end of line 14, my sequence is the element 6. When I've executed line 15, which says take the element 10 and add that to the end of the vector, well then my vector will be 6 and 10. And then as of line 16, it's 6, 10, and 17. One thing you'll observe is this very unusual syntax, which echoes something we might recall from C, the dot operator for structures, but isn't the same. Because in a structure in C, which is a structure is a bucket of data, all we can do is go in and look at what's there. Here, we're issuing a command, essentially. I'm telling the vector, go do this thing. The vector allows me to add elements to the end of it. In a sense, I'm sort of calling a function here, something we couldn't do in C with structures. And again, that's one reason why this is opening the door to a whole new set of operations and a way to view the world that we don't have in C. So what I'm doing is calling a function using the vector v. We can view the dot operator here as applying this pushback command, in a sense, to this specific vector v. I could have multiple vectors in my program, and which one I'm operating on depends on which one I've applied the dot to. Okay, what else can I do? Well, one of the other things I can do is v is a small appliance that takes care of sequences for me. I suppose I might want to know at some point, how many things are in the sequence today, v? And it turns out I can ask. I can actually ask v to tell me its current size. So I'm going to print that out. So the size is, and then I will ask v to tell me its size. And again, notice the dot notation. Okay, so the operation dot size, notice I don't pass in any arguments. I'm asking v to tell me something. I'm calling this function, v.size. It's going to tell me its current size and return that as an unsigned int. The size of a vector is unsigned because it makes no sense for a vector to contain a negative number of elements. All right, so I'm going to try that, and we'll just try running that in its current state. There we go. All right, so it compiled, it didn't complain. We'll assume that means it worked. It prints out the size is 3. Okay, now we'll do a little test quickly to make sure that it's not just making this up. So what if we only push in 2 elements? Well, then I suppose the size ought to be 2, and it is. Okay, that's a good sign. Now, of course, to really test this, I would want to find some way of actually printing out all 3 of these elements, but I am getting there. For now, though, it appears as if v is able to take my commands to add elements to the end, and later evidently respond to them, because I can ask it its size, and it does seem to keep its size up to date. So what else can I do? Print out the element at index 1. Now recall from C, and it's true in C++ as well, that the indexing convention is always to start our indexing at 0. So if I ask for index 1, I'm actually asking for the second element of the collection, so the number 10. If I'd like the vector to tell me a specific element, I can use this function called .at to ask it to give me the element corresponding to a particular index. So I'm going to try that out. The element at index 1 is, and then I print out v.at, and then I give it the index, v.at 1. Okay. And you will notice if you go looking for advice on the internet that there are all sorts of clever ways of getting an element of a vector. I would strongly encourage, if you can at all do so, to build the habit when you want the element at a particular index, always use .at. I know it's tempting to try and use some other clever method, but try and use .at. And so we'll try running that, and we'll hope that the answer, I expect the answer should be 10. It looks like it is. Okay, next question. So I've got this sequence of elements. I would like to iterate over my vector and print out every element. So what does it mean to iterate over a vector, or anything for that matter? So iterate over means I'd like to look at every element of my sequence. But that's not enough. I have to know what order I'm going to see them in. And it turns out that the goal of a vector is to store a sequence of values in whatever order I provided them. And so I suppose naturally, if I say iterate over the vector, what I expect is to iterate over them in the same order that I provided them, from left to right, from index 0 to the last index of the sequence. That's the natural order of a vector, the order the vector identifies with most naturally. And there are other ways I could choose to iterate over it. I could go over it backwards or from the middle out, but it makes sense if I stored the vector in this order, that that's the order I would want to use. And so keep that in mind. I know that's an odd way of me phrasing it, but it makes sense. The vector has one order that is the natural order of its elements. And it turns out C++ offers me a wonderful feature. This is a modern C++ feature since 2011 that allows me to iterate over a vector and just grab each element one at a time in the natural order. So in this case, from left to right. And it's a certain type of for loop. So the elements of my vector are all ints. So I'm going to write for int x, and then this colon, and then v. I read this as for each integer x in v. And then I'm going to write it, otherwise it's a normal looking for loop. This is a specific type of for loop called a for each loop. For each element x in v. So I'll just print out element, and then the value of x. The way that I've constructed this for each loop today, what I'm really doing is iterating over the elements of v. At each step of the loop, x is a copy of one of the elements of v. So that means if I modify x in here, the original inside the sequence does not get modified. We'll see there is a way of doing that next week, but we don't yet know the feature we would need for that. But in any case, it is very useful to be able to go grab each element in order without having to worry about indexing. But we still have the option of doing that. But first, we'll show this off. All right, so it prints out the elements 6, 10, and 17 in that order. I'm going to put an extra print statement here. Just to make sure that when I do task 5 that we don't get confused. Okay, so in task 4, I used a for each loop to grab each element of the vector. One really important thing to notice right now, a huge mistake that a lot of people make, it's a natural mistake, but it's a big disaster when you make it, especially on an exam, is to think that this for each loop tells you anything about indices. Well, no, it only tells you about the elements. It steps through the elements one by one. If I care about the index of an element, this for each loop is not going to help me. But if I just care about having a sequence of numbers, it's great. I don't need to worry about indices. I just grab each number one at a time. So notice for each int x in v gives me as the value of x a copy of 6, so there's 6, and then 10, and then 17. It doesn't tell me the index where it found those values. But if I want to iterate over by indices, like I would in C, I could write an old-fashioned C-style for loop that just loops over all the possible indices. Because I know how many indices there are. This vector has size 3. If I want its size, I can just ask it to tell me. And I know that the first index is 0 and the last index is 2. Or in general, the last index is the size minus 1. So I could write a for loop similar to the loop I might use in C to iterate over an array. I'm going to write it with an int first, and then we'll see that the compiler doesn't like that. I'm going to start my int at 0. I'm going to keep going while I is less than the size of my vector, and then I'm going to write I++ at each step. So I'm going to step through all possible indices. And then here we'll write element at index and then I print out the index, is, and then I print out the element that I can receive if I access the vector at that index, v.at I, and then I'll print out a new line. So I'm looping over all indices from 0 up to, but not including the size, and then printing them out. If I try to compile this, the compiler is going to get upset. So you'll notice that what it's complaining about is the condition. It's actually complaining about this. The issue here is that v.size is a function that returns unsigned int. Now, it's giving you a bunch of legalese here, but trust me on this, the operative part is unsigned int. Formally long unsigned int, even more formally this hideous incantation here. In this course, we're not going to worry so much about this. If you go on to write C++ as a career, you're going to need to learn to read things like this. What it's complaining about is I is an int, a regular int, with a sign. It could be negative or positive. v.size is an unsigned int, and the compiler is wary of letting you compare those things. There are reasons why this comparison can make a mess. Now, frankly, those reasons are irrelevant for this loop because the vector is small. However, as a matter of style, it is a good idea to get this warning to go away. And the warning is legitimate, so I'm saying we can dismiss it, but it's true that if the compiler has a good point here. It's just not relevant to vectors that are small. But in any case, we can make it go away by making our index variable unsigned int. Now the idea is the size of the vector is an unsigned int because the vector will never have a negative size. And by the same token, if I'm indexing the vector, why would I want a negative index? So I suppose it's reasonable that I would want to use unsigned int. And we'll notice that if I do this, that the warning goes away. You will be expected to have no compile warnings of this form on assignments. So please make sure you use unsigned int when you're iterating over a vector as well. There is an alternative, though. If you don't want to use unsigned int for some reason, and I don't know why that would be the case here, if you really want to avoid using unsigned int, you can also force the size of the vector to not be unsigned by using a cast. So I could do this. What this operation does is it says, get me the size of v, and then turn that value into a regular int. So force it into a regular int. Then when I do a comparison, this is an int, and this whole thing is an int, and so the warning goes away. It's true, many people will encourage that you do not use this style of cast in C++. There's a bit of a nuanced history there. In general, we call this a C-style cast. And like a C-style initializer, this style of cast is not always appropriate. But it is, I think, valid to use it here. A C-style cast is a valid part of C++. In general, this is not a good remedy to the problem that we just had. There are reasons why you would want to use an int index variable in a loop like this, usually because of things like iterating downwards from the end of the vector back to the beginning. But in this case, I think it's better just to make our index variable an unsigned int. And that makes the warning go away. We can see the warning is still gone. And so I'll try running the program and we'll see what happens. And it prints out the element in index 0 is 6, as we expect. Index 1 is 10. Index 2 is 17. All right. So, and as I said before, if I want to grab the element at a particular index, I use .at. Now, in the next video, I'm going to talk a little bit more about this. There is an alternative, but there are reasons why it's better not to use it, and I'll talk about that in the next video. In the meantime, I would like to do one more thing. I want to demonstrate one more wonderful feature of vectors, which is that they can grow and shrink as I see fit. And so what I want to do here is add another value to the end of my vector. So I'm going to say v.pushback, add the value 187. And so now my vector will have size 4. It should contain 6, 10, 17, 187. Then it says to repeat steps 2 through 4. So just to verify that we can, that the new value is actually visible inside the vector. So I'm going to copy and paste them. There we go. We'll just get rid of this and this. So I'm going to call this task 4 again. So I've modified my vector to add a new element, and now I want to print it out to verify that indeed that new element is actually there. So here I printed my 3 indices with my C-style for loop up on line 35. I then add the element 187 to the end. The size is 4. The element at index 1 is still the number 10 because I didn't modify what was already there. And then I print out 6, 10, 17, 187. And we can see the new element is indeed there. I want to do one last thing before the end here. It's not actually one of the prompts for this exercise, but I think it's worth doing. I want to do one last modification. So I'm going to perform task 4 once again afterwards, which is we've seen how to modify the vector by adding a new element. What about modifying an existing index of the vector? So pushback always inserts a new element at the end of the sequence. So if my sequence is 6, 10, 17, and I use pushback, pushback always increases the size of the sequence, so it adds a new element. But what if instead I want to modify some existing element? For example, I want to change element 10 to, index 1, which contains element 10, to be something else. Well, if I want to grab the element at index 1, I use .at. And it turns out that if I would like to modify that element, I can use .at for that as well. So let's modify the element at index 1 to be -999. And this is, again, very odd syntax. It echoes a lot of things we're familiar with, but it contains some stuff that just seems plain wrong in C terms. So how am I able to assign to what looks a lot like a function call? Now, it's a question we'll actually have an answer to very quickly in this course, but it looks very alien to us from a C perspective. What this is doing is it's saying, well, it's an assignment statement, so take what's on the right-hand side, that's -999, and assign that to whatever v.at1 is. Well, v.at1 would be this position here. So I'm going to take this position, I'm going to fill it in, remove the value 10 there, and then now it's -999. All right, when I print out the element at index 1, I should expect to see -999. And when I print out the whole sequence, I should expect to see this sequence here. So we'll try that out. And there it is. The element at index 1 is -999. And if I print the whole sequence out, I get exactly what I have over here. And so we've seen how to create a vector with integer elements and to perform various modifications to showcase all of the nice features of having a small appliance so that the vector can tell us its size. It can expand as we need. We can modify specific indices, and we can even iterate over the elements in an extremely convenient form with this for each loop. Now, it's still only a vector of ints, and so I guess have to prove the point that I can make a vector of other things, but also talk a little bit more about the best practices for working with vectors. I'm going to do that in the next video.